Hello. Today we will discuss various charge systems and electric field due to them. There are around 24 charge systems and we will discuss one by one to everyone. You are advised to make a chart for you so that you can take a quick revision. So come, let's start our journey. So electric field due to various charge systems. First is point charge Q. What is definition of point charge? Point charge is not the charge kept at a point, because you can't define point. Point has no volume, no length, no breadth, and no height. So its volume is zero. How can you put a charge on that thing which has zero volume? So this is a wrong definition. So we should come at the other definition. The smallest possible charge, which is smallest possible charge. So this is also wrong definition. Best definition is that charge systems due to which electric field is proportional to 1 by r square, those charge systems are called point charge. Okay, so we will say that point charge is charge system due to which electric field is proportional to 1 by r square. So it is very important. It doesn't matter whether it is very close to the charge body or it is far away. So come, let's see. Look at this point. There are two spheres. This sphere is uniformly charged hollow sphere, and this charge is distributed over the surface uniformly. There are 3 points. Point A is at the surface, point B just outside the sphere, and point C is just a sufficient distance from its center. So at surface you will say electric field at A is kq by r square. And at point B, just outside the sphere, you will say EB is equal to kq by r square. It doesn't matter that this point B is just outside or at some far away, at some significant distance. It doesn't matter. For this point B, this sphere will behave like point charge, because point charge has nothing to do with dimensions here. Point charge had to do that electric field due to which is proportional to 1 by r square, that will be a point charge system. So for point B as well as for point C as well as for point A, B, C, for all these points, this system will behave like point charge. And this is non-uniformly charged hollow sphere. For this, it will not behave like point charge, because this point charge system is for uniformly charged systems, not for this system, right? So let's come to the next point. Set first point is point charge Q. All the charge systems due to which electric field is proportional to 1 by r square is called point charge. I will say that when electric field is proportional to 1 by r square, then it is called point charge. If electric field is proportional to 1 by r cube, it is called dipole. And when electric field is proportional to, you can say it is constant everywhere, then you will say it is plate. For plates, it is not function of distance. So for point charge, electric field is equal to kq by r square. So come to next point. See, there are 3 figures, right? And there are 3 things here, number 2, 3, 4. This is very important. This 2k lambda by r is very important. This term comes into 3 places, comes at 3 places. First is charged arc. We have to find center, electric field at the center. This arc is making an angle alpha at the center. You have to find electric field at the center. Obviously, this electric field will be along the symmetrical line, and its value is 2k lambda by r sine alpha by 2. You have just multiply with sine alpha by 2 in this term. You will get the electric field due to an arc. This is formula for electric field at center due to an arc. In case of half circle, E is 2k lambda by r, because angle subtended at center is 180 degree. So you will say alpha is 180, 180 by 2 is 90. So sine 90 is 1. So this 2k lambda by r is electric field at center due to a half circle, means semicircular ring. Okay. And due to infinitely long wire having linear charge density lambda, electric field is 2k lambda by r. Lambda is coulomb per meter. It is charged per unit length or linear charge density. So this term 2k lambda by r is very important. It comes at three places. First, at electric field due to an arc at its center making an angle alpha at the center, and half circle it is 2k lambda by r, and due to infinitely long wire it is 2k lambda by r. So you will say they have same value, same formula. This infinitely long wire has same formula which has half circle at its center. So it is very nice that you have to just learn this term 2k lambda by r. You have to multiply by sine alpha by 2. You will get electric field at center of an arc. And the same term 2k lambda by r is used for half circle as well as infinitely long wire. Come to next point. Finite line charge. The same thing. K lambda by r. This is charge Q distributed uniformly over a rod having length L. So linear charge density will be total charge by total length. You can give your answer in terms of lambda as well. So E is K lambda by r. You know that when it will be infinite, then this alpha will just become 90 degree. So you will say that this alpha is 90 degree, then it was 2k lambda by r. So obviously when this infinite becomes short, then this length, this alpha is some finite, some less than 90 degree. So answer will be k lambda by r sine alpha plus sine alpha. So it's a special cases when wire is infinitely long. When wire is infinitely long, then your alpha is 90 degree. Then you will get your electric field as k lambda by r into 1 plus 1, that is 2, the same formula. So if it is of finite length, then electric field formula is k lambda by r into sine alpha plus sine alpha. I think in my view, when this alpha and beta are not symmetry, not equal, then I think in IIT JEE they will not consider it. So I'm not giving that formula because it will be very complicated, and I don't think that it is needful for IIT JEE. So come to next formula. Semi-infinite line charge. Okay, come just before you go at point this one. Infinitely line charge. What do you mean by infinite line charge? Infinite doesn't mean here that very long wire. Infinite means the point at which you are trying to get the electric field, that point P, is very close to this wire. If you are interested in find electric field at the point which is very close to this wire, then you will treat this wire as infinitely long. Infinitely long, it doesn't mean that it is infinitely long. So come, let's see. Semi-infinite line charge, it means electric field due to this semi-infinite line charge at point P is, it has two components. One is parallel to the wire, E parallel, and one is perpendicular to the wire, and that is E perpendicular. Both have same values, k lambda by r and k lambda by r. Okay, both have same values. So net electric field will make the angle 40 degree with this line. So you have to remember this. E perpendicular and E parallel both are k lambda by r, and E net is k lambda by r root 2, right? So this is very important result you have to learn. Come, let's discuss the electric field due to very charged rod along its axis. It is very, very important, and it is very interesting also. So you can say that there is a rod having length L. It is uniformly charged, having charge Q. So you will define lambda, that is uniform, that is linear charge density, that is Q by L. So electric field, I will suggest you that you learn this formula in this way. There is a result, very important result, that when this L is very small, then it behaves like point charge at P. Means when A is much greater than L, A is much greater than L, means L is much less than A, then it behaves like point charge. So E is kq by L. This is very small, L is very small, and you have to find electric field at point A. So formula is kq by A square. But you have to find when there is L is some finite significant length. So what should you do? That kq by A square is the formula for the point charge, and just you remember L by A plus 1 into, you have to multiply by this term in denominator, L by A plus 1. So kq by A square into L by A plus 1. This is the result you have to remember. Means first to remember for the point charge kq by A square if L is much less than A, and then if it is finite significant length, then you have to multiply by L by A plus 1 in denominator. Now you can give your answer in terms of lambda also. Obviously lambda is q by L, total charge by total length. So you will put in place of q, this is lambda L, and now you will write A square into L plus A by A. This A will be cancelled out. You will get k lambda into 1 by A minus 1 by L plus A. So I will suggest you to note down all these two formula, this and this. You can answer in both ways, whatever he wants. So if you can answer in terms of q, you can answer in terms of lambda. So but it is easy to remember in this term, that first you write point charge, then just multiply by L by A plus 1 in denominator, right? Now this term is also very important, like 2k lambda by r. 2k lambda by r was this term, so it was important here. 2k lambda by r was important for the arc, half circle and infinitely long wire. But this term kq by r square plus x square to the power 3 by 2, it is very important for two things. First, at axis of uniform charge ring, at axis of uniformly charged ring, this is a ring, it is uniformly charged. You have to find out electric field at the axis, which is at point P, which is distance x from its center O. So you will get the formula E is equal to kqx by r square plus x square to the power 3 by 2. And you will get the same result. It is very interesting. In IIT JEE, they have asked 2 times this formula, actually 2 or 4 times. When sometimes they ask for time period, sometimes they ask for electric field maximum value. So you have to remember this so that you can solve your problem in 15 seconds. So this term also comes when at perpendicular bisector of 2 point charge. There is 1 point charge, there is another point charge, and this is perpendicular bisector. You have to find electric field at point P, which is at a distance x from its this point O. So you will use the same formula, E is equal to kqx by r square plus x square to the power 3 by 2, and that q, in place of q there is only one change. In place of q you will write these both charges, plus q and plus q, 2q. This is only difference, but formula remains same. All the pattern, this all the symmetry is here. So you can write 2q in place of q. There is difference. So it is very important to learn it. Next, electric field at the axis of uniformly charged ring. This is uniformly charged ring. You just observe that electric field at the axis is kqx by r square plus x square to the 3 by 2. So I will give an idea. I will say one thing, that when all this charge is running, then all this charge is revolving around the circle, then you will get a current here. Then you will be asked magnetic field at its axis. This electric field axis is like this. This magnetic field axis will be like this. It will be also same direction. So you know, just you observe, B axis is formula mu naught I r square by 2 r square plus x square to the 3 by 2. You have to observe these two formulae. Just observe. When charge is static and kept at the ring, then you have to learn this formula, kqx by r square plus x square to the power 3 by 2. And when charge is revolving in a circle, then you will get a current and you will find magnetic field here. So B axis is mu naught I r square by 2 r square plus x square to the power 3 by 2. You have to just observe and remember this formula. You can notice here that here is x and here is x in denominator as well as in numerator, but there is x only in denominator. So to get maximum value of electric field, you have to differentiate at this function and you will keep it 0. Then you will get that it is maximum at x equal to r by root 2. But for this function to be maxima, you are not to differentiate. You can say easily then this b is maxima when x is minima, and x square is minima is 0. So its maximum value is at 0 at the center of the ring, and in this case its maximum value is x equal to r by root 2. So when we will discuss the chapter of magnetic field, then we will say that b axis is mu naught I r square by 2 r square plus x square to the power 3 by 2, and it will be maximum at x equal to 0, and this will be maximum at x equal to r by root 2. So what you should do, that you should clearly understand that when charge is static, there will be asked for electric field at the axis. When charge will move in the circle, then you will ask for magnetic field at the axis, and its formula should be remembered badly so that you can write immediately. It has been asked a number of times in IIT JEE. So come, let's discuss another point. This is electric field at the axis of a uniform charge ring. The same thing, that function was kqx by r square plus x square to the power 3 by 2. So this function, when you will differentiate, d by dx will be equal to 0, then you will say that x equal to r by root 2. Its maximum value is at x is equal to r by root 2. At this point, electric field is maxima, and its maximum value is 2 by 3 root 3 kq by r square. 2 by 3 root 3 kq by r square. And at this point, electric field is in positive x direction, and at this point electric field is in negative x direction. So graph is here in y axis and graph is here in plus y axis. So this is graph of electric field vector of an uniformly charged ring at its axis. So you have to remember that electric field has maximum value at r by root 2, and maximum value of that electric field is 2 by 3 root 3 kq by r square. At perpendicular bisector of 2 point charges, the same thing happens when there are 2 point charges having distance d between them, and you have to find that point at which electric field is maximum. The same graph will appear here, and x is r by root 2. Okay, x is r by root 2, and you will say that r is here radius. This distance d is 2r. So d is 2r, so r is d by 2. So the point at which electric field will be maximum, that will be r by root 2, and you can put r is equal to d by 2 here. So x equal to d by 2 root 2. So d by 2 root 2 is that point at which you will get the electric field maximum. So just be alert and just note that we will not write that it is d by root 2. If radius was d, this was d, then you will say that this is d by root 2. Otherwise, if distance between these point charges is d, it means 2r is d. It means r is d by 2. So you will write that maximum value will be at x equal to r by root 2. It has been asked in IIT JEE. Okay, next. Yes, now we will come at this term, sigma by 2 epsilon 0. What is sigma? Sigma is surface charge density. It is charge per unit area, that is q by a, right? It comes at 5 places in physics, right? First, just outside the conductor. First you should say sheet of charge. Sheet of charge. Due to a large sheet of charge, electric field is sigma by 2 epsilon 0, right? And number 1 is sheet of charge. Number 2 is conducting sheet of charge. Obviously, conducting sheet will have 2 layers. That is, there are 2 layers. So one is sigma by 2 epsilon, another is sigma by 2. You will add up, they will be add up here. So you will get sigma by 2 epsilon. And number 1, electric field just outside the conductor will be sigma by epsilon. And due to disk, you will at the axis, you will get the electric field at the axis. I will write the formula at the next page. and there are two opposite charge plates, plus and minus. So inside, at this point, positive will repel, minus will attract, net field will be 0, and at this point plus will repel and minus will attract, so net field will be just, it will be sum up sigma by 2 epsilon 2 times, you will get sigma by epsilon. So this term sigma by 2 epsilon is very important. So I will summarize that there are three terms we have used. First is lambda by 2k lambda by r. It was used at three places: arc, semicircle, and infinitely long, right? And next term was kqx by r square plus x square to the power 3 by 2, and it has been used for two times. First, it has been used for two places, at two places. One is this ring at its axis for the electric field, and another, there are 2 point charges plus q and plus q, equal point charges, and we have to find electric field at the perpendicular bisector of them at point P. So you will get the same formula. And now I am discussing the third term, that is sigma by 2 epsilon 0 or sigma by epsilon 0. What was sigma? Sigma is surface charge density. Sigma is surface charge density, that is charge per unit area, that is q by a. When charge is distributed at length, then it is called linear charge density, and if charge is distributed on area, then it is called surface charge density, and it is distributed on volume, then it is called volume charge density. So we will discuss this. Okay, see, this sigma by 2 epsilon 0 appears at 5 places. First is sheet of charge. There is large sheet of charge, electric field due to which is sigma by 2 epsilon, right? Sigma is charge distribution on its plate. You can say this is non-conducting sheet because it is single layered, non-conducting sheet or sheet of charge. You can say there is conducting sheet of charge. Obviously there will be two layers. Due to first layer, electric field is sigma by 2 epsilon. Due to this layer is sigma by 2 epsilon. They will sum up and give you sigma by epsilon, right? And axis of uniformly charged disk, you will say electric field is this term sigma by 2 epsilon. Actually disk is part of this non-conducting sheet, so it will be fraction of this, sigma by 2 epsilon, and what fraction was 1 minus cos theta. You have to find electric field at this point P. This is x, this is r, so you will write cos theta is this by this. You can use Pythagoras to get this thing. So sigma by 2 epsilon into 1 minus cos theta. So cos theta will be base by hypotenuse, that is x by root of r square plus x square. You can get this term somewhere else, electric field just outside a conductor. It is sigma by epsilon, not sigma by 2 epsilon. You can see that these two results are the same, sigma by epsilon here and sigma by epsilon here. Actually they are the same. Electric field just outside the conductor is always sigma by epsilon 0, either in this shape or in this shape. An electric field due to capacitor. Capacitor is a system of charges. It is a system in which we keep energy. There are two plates. On one plate there is plus q and another plate is there is minus q. So electric field just outside this plate will attract and this plate will repel. So electric field is 0. At this point plus will repel and minus will attract. So you will say that you will get sigma by 2 epsilon plus sigma by 2 epsilon. So these two will give you sigma by epsilon. So electric field inside the capacitor plate is sigma by epsilon, right? So this is very important to understand. The electric value of sigma by 2 epsilon 0 comes at 2 places, comes at 5 places in physics, right? So we will discuss the next. Hollow charge systems. There are three systems you can see. One is hollow sphere, another is hollow cylinder, and last is hollow thick plate. So this is hollow sphere, charge is distributed over its surface. This is hollow cylinder, charge is distributed on its surface. and this is hollow plate, a thick plate. One layer is here, another layer is back of this another sheet. So you can say कि in this case the hollow charge systems electric field inside is 0. Here electric field is 0, here electric field is 0, and here also electric field is 0. So electric field inside is 0 when there is hollow charge system. It is obviously uniformly charged. So you can see I have plotted the graphs here, right? Electric field inside is 0 here, electric field inside is 0 here, electric field inside is 0 here. Whenever you will get hollow systems, there is electric field inside them is 0. But outside the sphere, it will behave like point charge, that is proportional to 1 by r square. Outside the cylinder, it will behave like line charge, right? Cylinder will behave like line charge. Its value will be 2k lambda by r. And at the plate, this plate will behave like a constant electric field, and its value will be sigma by epsilon. So it is very important to understand that whenever uniformly charged system is there, then any field, whether electric or magnetic or gravitational, everything will be 0 inside a uniformly charged system. So electric field is 0 inside this uniformly charged system, and for the sphere it will behave like point charge outside, and for the hollow cylinder it will behave like line charge outside, and for the thick plate it will be constant. So we will discuss next. Uniformly charged systems, obviously non-conducting. Uniformly charged systems, obviously non-conducting. So we should understand that whenever there is conducting body, then all excess charge comes outside at the surface of the body. So there is no excess charge inside. You can't put excess charge inside the conducting body. So all these three you can say are the conductors. But if there is non-conducting, uniform distribution of charges, then you can say you can put charge inside. Whenever you can put charge inside, then you will say that this system is non-conducting sphere or non-conducting cylinder. So you can see here that there are three systems. First is solid, there is non-conducting sphere, and second one is non-conducting cylinder, and third one is non-conducting thick plate. So you have to be asked that you find the electric field inside and electric field outside. Obviously electric field outside will not change, because it doesn't matter whether you are having hollow or solid system. Electric field outside will be the same. For the sphere it will behave like point charge, like kq by r square, and for the cylinder it will behave like line charge, 2k lambda by r, and for this it will be constant. But inside they will grow linearly. It is true for all the fields, whether it is electric or gravitational or magnetic, for all the fields. It will grow linearly here, it will grow linearly here, it will grow linearly here. So electric field is varying linearly, it is growing linearly in all these systems. All these systems are solid, or you can say non-conducting. You have just filled them with the charge. You will see that electric field is maximum at this surface. When you move away from the center to the infinity, then you will say electric field increases, then it reaches to maxima at the surface, then it decreases, and slowly it becomes 0 at infinity. So it is very important. In case of hollow spheres, this electric field inside them will be 0, and outside they will have like point charge or line charge. And in case of solid non-conducting spheres who are filled with charges or masses or current, then any field, whether electric, gravitational or magnetic, everything will grow linearly inside that system. And you can use similar triangle here to get electric field. E inside is here and x is here. Here is E surface and R is here. You can say this by this means E in by x is equal to E surface by R. So you can say E in is equal to E surface into x by R. This is very important. It is very important. It is obviously, it comes from the Gauss law and Ampere's law, but we can use easily with the help of similar triangle that E in is equal to Es into x by r. I have used frequently this formula for the gravitational field as well as magnetic field. So we'll discuss this in gravitational field again. This formula, it is not formula, just use of similar triangles. It will just increase in the same ratio. So x will increase by r to r and E in will increase to Es. So ratio will be same. There will be photographic enlargement. This triangle will be photographically enlarged. You can say their ratio will be same. It's very important. When charges are filled with the, when these systems are filled with charges, then we will say that inside electric field will grow linearly. It is very important. And when they are hollow, uniformly charged hollow, then electric field inside them will be 0. Okay. Electric field due to a dipole. What is a dipole? When there are two charges, minus q and plus q, are kept at some distance, this is called dipole. And when we are interested in electric field at point far away from this system, then it is called dipole. So dipole means having two poles, minus q and plus q. P vector is dipole moment vector. You will not use this system. You will say that this system has P vector is dipole moment vector. We have to introduce a new term, P vector, that is dipole moment vector. So we should understand the electric field lines due to these two systems. So this is dipole moment vector, and there are two positions. One is the axial position. This is along the dipole. This is across the dipole. It is equatorial position. To the axial position, you will say end side on position or broad side on position. End side on position or broad side on position. So axial position is called end side on, and this equatorial position is called broad side on position. So you see electric field lines emanate from positive, from this positive. This dipole moment is from minus to plus in physics and plus to minus in chemistry. We are discussing here in physics, so we will take its direction from minus to plus. So from positive, electric field lines emanate, and at negative they will terminate. So you can see that at equatorial point, electric field is opposite to direction of P. Direction of electric field is opposite to direction of P. So E axial, and here electric field is parallel. Electric field is parallel. So at axial position, electric field is parallel to P. Electric field is parallel to P, whether it is in front of dipole or in back of dipole. So at both points, electric field is parallel to P. And you can observe that at this point, equatorial position, electric field is in this way and opposite to P. So at E axial is parallel to P, like this and this, and E equatorial is anti-parallel to P, right? So electric field due to a dipole, you can see here there is a dipole whose dipole moment vector is P, and there are 4 points A, B, C and D. You have to show the direction of electric field at these points. Since point A and B are on the axial position, so their electric field will be parallel to P. So electric field at A will be along the P. This is parallel to P. And since C and D points are at this equatorial position, they are anti-parallel to P. So electric field will be in this way and in this direction. So at point A and B, electric field will be parallel to P, and at point C and D, it will be anti-parallel to P. Now we come at electric field due to a dipole at general point A, r theta. So we will discuss electric field at general point r theta. So see, here is a dipole P. Now we have to find electric field at this point A, right, which is kept at an angle theta with the direction of P at distance r, right. We will just resolve this dipole P in two parts, along the r vector and across the r vector, right. So obviously this is P, so this will be P cos theta, and this will be P sine theta. You have to find electric field at this point A. This, due to this P cos theta, it is its axial position. The axial, at an axial position, it is 2k P cos theta by r cube. We have just find here that electric field at axial position is 2 kp by r cube. This is formula for the axial position, 2 kp by r cube, and electric field at equatorial position is kp by r cube. Obviously it is half of axial electric field. So axial electric field is 2 kp by r cube and equatorial is kp by r cube. You can say that electric field at equatorial will be equal to minus of half of electric field at axial. Its direction will be opposite to that of electric field at axial point, and it is in the opposite direction as well as half also. So now come to this point. There is a dipole having dipole moment P, and you have to find electric field at point A, which is at some angle theta, making angle theta at some distance r. So we will resolve this P along the r and across the r. This along component will be P cos theta, right, and across component will be P sin theta. So this P cos theta, due to this P cos theta, this at point A you will get electric field, this component will be 2 kp cos theta by r cube, because look here, at the axial position electric field is 2 kp by r cube. So due to this dipole component, it is axial position, it will be, formula will be used here, 2 kp by r cube. So 2k, at place of P you will use P cos theta by r cube, and at this point, due to this dipole, electric field at this point A will be opposite to P, and like this, kp by r cube. P is P sin theta, kp by r cube and 2 kp by r cube. This is axial position, 2 kp by r cube. This is equatorial position, and at this point it will be opposite to this, kp by r cube. And in place of P you will use here P cos theta, and in place of P here you will be use kp sin theta by r cube. So this is E1, this is E2. You will make the parallelogram here. This is E net. Obviously these two sides are equal, so this will be also kp sin theta by r cube. This is 2 kp cos theta by r cube. You can write tan alpha is this by this, perpendicular by base. You will, this kp by r will be cancelled out. This is sin theta by 2 cos theta, means tan theta by 2. So you will get tan theta by 2. Tan alpha is tan theta by 2. You can observe here that angle between r and p, r vector and p vector is theta, and angle between E net vector and r, see, E net vector is here, r is here, so angle between E net and r is alpha, right? And angle between p and E net is, p is here, E net is here. First you rotate in this direction, theta, then again alpha. So angle between E net and p will be alpha plus theta, right? So this is the angle, and you can get tan alpha here, that is angle between r vector and this E net, that will be tan alpha, and that will be this by this, that is tan theta by 2, and E net will be this, that you will take this common, kp by r cube, kp by r cube. So you will get kp by r cube into sin square theta plus 4 cos square theta, sin square theta plus 4 cos square theta. You take 1 cos square theta here, then you will get 1, and that will be 3 cos square theta. So this is electric field formula, magnitude of that electric field at point A. It will be kp by r cube into root of 3 cos square theta plus 1. It is formula at general point A, electric field due to a dipole. So now come at electric field. There is one interesting question. Just I forgot that. There is one very interesting question. Question is that, suppose there is a dipole having dipole moment P. You have to find the position of that point, angular position of that point A, at which electric field is perpendicular to P. Electric field is perpendicular to P. You have to find the position, angular position of that point A. Obviously, angle between P and E was angle between P and E was theta plus alpha. So you will say that alpha plus theta is equal to 90 degree, right? Because this was P, this was theta, and this was alpha. So angle between P and E net was theta plus alpha. That was 90. And alpha is equal to 90 minus theta. So you will write tan alpha is equal to tan 90 minus theta. And tan 90 minus theta is cot theta. So this is equal to cot theta. And tan alpha was in formula, you just observed here that tan alpha was tan theta by 2. So you will write tan theta by 2. It will become tan square theta is 2. It means tan theta is root 2. So theta will become tan inverse root 2, right? So this is the angular position of that point at which electric field will be perpendicular to dipole moment vector, right? Now we will come at electric field due to a conductor. It is very important property, right, that electric field due to a conductor is, there are some properties. Excess charge inside conductor is 0. Excess charge inside conductor is 0. There is no charge inside. Excess charge resides on surface of conductor. See, excess charge has appeared at the surface of the conductor. And now third, electric field inside conductor is 0. And fourth, electric field just outside conductor is sigma by epsilon. I have discussed this earlier also. So these are 4 very important points for the conductor. First, excess charge inside conductor is 0. Electric field inside conductor is 0. No electric field line can penetrate the conductor. And the electric field just outside the conductor is sigma by epsilon. But this is true only in electrostatics, not in current electricity. In current electricity, there is a conductor. You just apply a battery, maintain a potential difference across its terminals. There is electric field inside conductor. So there is electric field inside conductor in current electricity, but in electrostatics, there is no electric field inside conductor. So you will say that excess charge, there is no excess charge inside the conductor. Excess charge appears at the surface of conductor, and electric field inside conductor is 0, and electric field just outside the conductor is sigma by epsilon 0. Okay. Some more about conductor. This is a conducting body of irregular shape. You can see that at point A, if you make a circle, this radius at A is less than radius at B. So curvature is more at A. It is more curved at A. It is more straight at B. So radius is more at B and less at A. You can just see RA is less than RB. At conductor, sigma into R is constant. Where the R is more, sigma will be less. So you see sigma is surface charge density, and there is more leakage of chance when sigma is more. So when RB is greater than RA, so obviously R is more, then sigma will be less. Sigma at B will be less than sigma at A. So electric field will be stronger at A because electric field is sigma by epsilon 0, and sigma into R is constant. So at A, R is less, sigma will be more, so electric field will be more. So you can be asked about the strength of electric field at point A and B also. If at you have to find that whether electric field is stronger at A or B. So you will say that it is stronger at A. Okay. Now come at this point. It's very important point. This conductor is spherical. So charge Q is distributed over this surface. It is having radius R. You can say electric field just outside the hollow sphere. So you know that formula is KQ by R square. But I will say it is again true sigma by epsilon 0. Because electric field near conducting plate, or electric field near conducting sphere, or electric field near any conducting body is sigma by epsilon. So electric field just outside the hollow sphere is kq by r square or sigma by epsilon, right? You can prove it also. Kq by r square, sigma is total charge by surface area, total charge is q, surface area is 4 pi r square. So kq by r square, k is 1 by 4 pi epsilon 0, q is sigma into 4 pi epsilon square. We will solve it, we will get sigma by epsilon. So electric field just outside the hollow sphere is not only kq by r square, but it is sigma by epsilon. It is very, 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 very important, right? Now about conductors, we have taken some patch from here. It is blank, right? There is nothing. There is a sphere, uniformly charged hollow sphere. Some patch, very small patch we have taken out. Now a small patch is removed. Now you have to find the electric field due to all this remaining part at this point. So answer is sigma by 2 epsilon. Let's see how it comes. See, there are two parts. One part, A, is called this patch which you have removed, and B, the remaining part of the sphere. We know that electric field due to these two both systems, when you will put it at the gap, then it will make a complete hollow sphere, and you see that electric field just inside this hollow sphere is 0. So whatever be the electric field due to this A part will be in this direction, the remaining part will be just in opposite direction to cancel it, so that electric field is 0 inside this sphere. And just outside the sphere they will be just EA and EB. Inside they are EA and EB in opposite direction. Inside the sphere they are in opposite directions, and outside the sphere they will be in the same direction. And here they are cancelling out, EA and EB are just 0, and just outside they will just add up, they will give resultant, and that will be sigma by epsilon. You know that electric field just outside the sphere is sigma by epsilon, right? So these two things, A and B, will together they are giving sigma by epsilon, or inside they are cancelled out. So inside they are equal, outside they are adding, so inside they will be equal. So EA is EB, here you can say EA is EB, together they are giving sigma by epsilon. So EA is EB is sigma by 2 epsilon. So whenever some patch is removed, then electric field due to remaining part of sphere will be sigma by 2 epsilon, right? It is very interesting. Electric field inside charge free cavity. So it is very interesting. Electric field inside charge free cavity. See, inside conductor, if there is conductor, you are putting a charge Q. Obviously all charge comes at the surface, it appears at the surface. This cavity has no charge, nothing will happen. Nothing will happen inside cavity. Electric field will be 0 and charge will be 0. This is charge free cavity inside a conductor. Now let us think inside non-conducting. Non-conducting means uniform distribution of charge. Charge is uniformly distributed. So there is a cavity, spherical cavity inside a non-conducting sphere which is uniformly charged. Center of the sphere is C1, center of this sphere is C2. So inside, electric field inside this cavity will be uniform. In this cavity it will not be 0. Here it is 0. Both cavities are having no charge. In this cavity electric field is 0. There is no charge, no electric field. In this cavity, although there is no charge, but there is electric field. We will discuss in detail in Gauss law how it happens. And electric field is uniform inside this cavity in magnitude as well as direction both. So uniform distribution of charge is non-conducting, and in here you get inside the cavity uniform field which is uniform in magnitude as well as direction. What will the answer? There is center C1, there is center C2 of the cavity. Electric field inside this cavity will be parallel to line joining C1 C2. If this vector is A vector, if C1 C2 vector is A vector, then electric field inside the cavity will be rho A by 3 epsilon 0 in the case of a sphere. And you can see that here there is cylindrical part, there is very cylindrical cavity, small cylindrical cavity having its axis at position A vector from this main axis. Now electric field inside will be rho A by 2 epsilon 0. It is the same formula which was for the complete sphere or complete cylinder. So you can say whenever there is cavity, charge free cavity inside conductor, so electric field and charge both are 0. But in case of non-conducting sphere, charge is 0 but electric field not 0, and electric field is uniform here, and that electric field is parallel to line joining the both. And at this point P, see, it is very interesting, it has been asked in IIT JEE that at point P, if this position is R1, this is A, so electric field will not depend on R1. Electric field will not depend on R1 because it is independent of the location of point inside the cavity, because it is depending only on the this C1 C2 vector. It is not depending on the location of that point. It is independent of R1. Okay, now let's come at another point. Electric field due to a hollow hemisphere. You need not to remember this result, but electric field at center is sigma by 4 epsilon. Hollow hemisphere, electric field at center is sigma by 4 epsilon. And it is very interesting, this B is off center, it is not at the center, it is off center, but direction of electric field is not in this direction, not in this direction. This is not correct, this is not correct. It is very important to understand and to know and to remember and to learn that electric field at point B is perpendicular to this plane surface, because this surface is in further you will see that this surface is equipotential and electric field lines are perpendicular to equipotential surfaces. So whether is point A is at center and B is off center, both are at both points electric field is perpendicular to the surface. So E1 is perpendicular to surface, E2 is perpendicular to surface. Their values are not equal. They are not equal in values, because at center you will get sigma by 4 epsilon, at E2 you will not get, but it is perpendicular to the surface. B is off center and direction of electric field will be perpendicular to the plane surface. You have to remember it. When we will discuss potential in the next lecture, then we will understand it completely. So come, let's discuss a very nice question. Uniformly charged hemispherical shell. There is a uniformly charged hemispherical shell. We have divided it in 3 equal parts. See, these angles are equal. First part is here. This part, there is one slice. There is another slice. I have named it 2. And there is last slice, third. I have named it 3. So all this hemisphere is giving electric field E0 at center. All these alpha beta are equal and they are 60 degree. So it is given that uniformly charged spherical body is just, we have mentally cut it into 3 parts, 3 identical parts, and these all are giving electric field E0. Then find out electric field at center due to one of any one part, due to any one part, either due to 1 or 2 or 3, right? Whether it is E0 by 2 or E0 by 3 or E0 by 4. It is very interesting. See, electric field due to this part will be along the symmetrical line like this, E at 30 degree, some 30 degree, 30 degree with the vertical here. And electric field due to this part will be like this. Suppose it is E1, this is E1, it is also at 30 degree, and electric field due to this part is again symmetrical, E1. See, this E1 and E1 are at 60 degree, right? So E1 and E1 are 60 degree, and they are just making some angle. I think they are making some angle. This is 60 degree and this is 30 degree and this is 30 degree. I think they are making angle some 120 degree, 120 degree. This angle is, they are making 120 degree. This angle is 120 degree. So this E1 and E1 has resultant E1 also, right? And this E1 and this E1, they together are giving value E0. So you will say that 2E1 is E0. So E1 will be E0 by. It is very nice question. You can just solve it by concept of using vectors, that if one part is giving electric field this side, second part is giving this side, one part is giving this side, all these 3 vectors are giving electric field E0. So obviously we will not resolve E1 and E1 having angle 120 degree, their resultant will be E1. So E1 and E1 was together, it was called E0. So E1 individually was E0 by 2. It was very nice question. And this is very, very interesting question. This is a non-conducting, obviously, Non-conducting, you are putting charge inside the sphere. Non-conducting uniformly charged sphere having volume charge density rho, right? And radius of sphere is r. There is a point P outside here. Location of this point P is, it is a distance 2r from the center. You have to find electric field in terms of rho. See, this point is outside the sphere, so electric field is just point, it will behave like point charge. Kq by r square, small r is 2r, so kq by 2r square. So you will write k is 1 by 4 pi epsilon into q is 4 by 3 pi r cube volume into rho, and this 2r square is 4r square. So you can solve 4 and pi and r square with r, so you'll get rho r by 12 epsilon 0. So electric field outside of this sphere at point P will be rho r by 2 epsilon 0. So now come to the last question of this lecture. It is very important and very nice, so we will discuss it. Very important question and very nice question. There is a uniformly charged non-conducting hemisphere. It is non-conducting, so you have kept charge inside the sphere. Its volume charge density VCD, volume charge density is rho, and there are 2 points at equal distance from this O. From this O there is a point A at distance 2r. From this O there is a point B at distance 2r. So if electric field due to this charge system at A is E, due to this charge system electric field at A is E, right? Then find the electric field due to this at B. If electric field due to this charge system at A is E, then you have to find electric field due to this charge system at B. It is very simple and very nice question. See, I'll solve it. It is the last page of our discussion. So see, I will complete this sphere first and just put charges inside this. So you have just calculated that due to this both system 1 and system 2, due to both system it is a complete sphere, and you find electric field at point A was rho r by 12 epsilon, right? So you will say that due to this system and this system together at point P, at point A, this due to this system it was E, and together it was this, and due to this system it was E1, and due to this system it was E, it was given, and E1 plus E together were giving this much. So E1 plus E together were giving rho r by 12 epsilon. So obviously E1 will be rho r by 12 epsilon minus E. Very interesting thing. So in the back of this hemisphere B, you are getting E1. It is the same problem. It is the same location. For this hemisphere, this point has same location which this has for this hemisphere. So it is very nice question. So you can complete it by using another hemisphere, and due to complete sphere there is electric field at this point, and this sphere is due to this electric field due to this plus due to this, and due to this it was given E1 E, and due to this you have to find. So this plus this was this much, so E1 was this much. What this hemisphere has electric field at this point is the same as this hemisphere at this point. So I have discussed all these electric field formula for you. It will be very important in the IIT JEE and as well as JEE Main and Advanced, and for NEET also. Not all questions in NEET will be important, but around 80% questions will be important for NEET. So it is very important to just learn these 24 problems, 24 formulae, so that you can immediate recall in exam, and so that you can solve your question within 15 seconds and 30 seconds. So I hope you have enjoyed this video, and if there is some suggestion, please give in your comment section, and thanks for watching this. Thank you again.